So let's get started. Let's picture this scenario. A company releases their synthetic financial data set publicly. They've got differential privacy guarantees, epsilon set at 8, all the mathematical protections in place, and they're thinking, we've got DP, what could possibly go wrong? Well, it turns out quite a lot could go wrong, and all it took was some grad students with their laptops and local compute to find it out. Speaking of which, I'm Yash Maurya, and this is Aman Priyanshu, and we conducted this research during our time at CMU, and yes, we're part of the classic PEPR resource model, grad students as a service. And how many of you have worked with synthetic data before? Could I get a show of hands? Okay, quite a lot. And how many of you feel completely confident about the privacy guarantees you're getting, if any? This is what we expected. Okay, so let's take a step back and get everyone on the same page of what synthetic data is. So what exactly is synthetic data supposed to do for us? The promise is beautiful, right? You get data that mimics real distributions, enables statistical computation, attempts to have no direct linkage back to the individual. It's supposed to be the holy grail. You never have to choose between quality and privacy because you can have both. And we desperately need that to work. We're using synthetic data for everything at this point. AI model training, particularly LLMs, data augmentation for sensitive domains like healthcare, sharing with third parties, research, experimentations. The use cases are exploding. I'm sure you all have better use cases than these too. But here's the thing. There's still a big problem which keeps on happening. Training data can leak. And when you're using pre-trained LLMs to generate your synthetic data, which is increasingly common at this point, you're not just dealing with your training data anymore, you're dealing with everything that the LLM learned from the internet. And that's a lot and so much more stuff there. And okay, so what about DP? Could we add that here? So DP is supposed to solve this problem. It gives us mathematical guarantees, formal privacy definitions, but as we see today, there's often a gap between theoretical guarantees and empirical privacy if not applied correctly. Here's a case study. And so let's just, so we decided to test this gap armed with our laptops again and the determination to see that what could go wrong. We found a differentially private synthetic financial data set on Hugging Face with over 1,000 records. This was generated from over 14,000 public SEC filings. This was a substantial synthetic data set with formal privacy guarantees, which we are supposed to be trusting. And this is something new which we found, so we dove deeper into it. And here's what we knew going in this analysis. Public SEC filings from 23-24, generated using a 5.3 mini model, differential privacy DP-SGD with epsilon as 8, and document level privacy units. All the right buzzwords, right? All the right protections. But here's where things get interesting. The original dataset description didn't mention privacy unit, delta value. These are critical parameters for understanding what kind of guarantees does DP actually provide. When we dug deeper into it, we found that they use document-level privacy units. Think about that for a moment. In a financial data set, where there are multiple documents coming from the same company, shouldn't the privacy unit be at organization level? Each company has multiple SEC filings. The DP mechanism was treating each document independently. That's like putting a lock on every page of the book instead of protecting the person who wrote it. So then we put our adversarial hats on and we asked ourselves, if we were security researchers who just stumbled upon this data set, what could we possibly extract? What would happen if we treat those mathematical guarantees skeptically? And results? Well, let me hand it over to Aman, who's going to walk you through exactly what we found out and how we did this systematically.
Thank you, Yash, for the adversarial hat. So let's begin by something which I'm sure all of you all are innately familiar with, the black box threat model. So this is definitely the most realistic expectation of adversaries or like threat models in the wild, where you're expected, like it's an external researcher with the access to the data set or a malicious threat actor who wants to look at the data set and infer things about the training data itself or your fine-tuning data itself. So in our case, we did not have any exact ideas about, say, the training process, what kind of models we're using other than the phi model itself, whether it was LoRa or some other kind of fine-tuning, just the data set itself and some basic analytical tools, and we started with that. So our primary goal is that this is a differentially private synthetic data set. So with that information in mind, could we still reveal anything sensitive? Or how well did these DP protections hold? So something about the domain itself. We knew that this was a financial domain data set, which means things like organizational name, partner names, executive names were kind of expected as being part of the distribution itself. So that's the first attack vector we looked into, which is PI identification. We looked at 3 low-resource NER models. I mean, we are still grad students at the time, and we couldn't use things like OpenAI or some big LLM. So we stuck to Presidio and Spacey, and some Glino models, which are transformer-based recent models for NER extraction. One of them actually belonged to the same organization which released this data set. In our analysis, we found that simple models within Spacey themselves could extract 100 times more names or NER named entities, and in a much faster way than the transformer models themselves. One of the key insights we take away from this is that even before launching of this data set, PI extraction should have been occurring at the synthetic data level itself, because even though it might have been redacted during training, we don't know how the fine-tuning might have unlocked from the similar distribution of sensitive data. Moving forward, we looked at clustering analysis, where we used sentence transformers to create representations, which allowed us to analyze whether these documents found some kind of internal clusters or like distributions where we could match things. We knew that they were formed from 3 specific SEC style documents. However, we found that in our analysis, we found that there were 8 clusters being formed. Now, this could be due to the natural distribution of the dataset itself or differential privacy. Same thing with distribution analysis, where we found that a normal distribution was being formed for specific sequences or term phrases, which we use for analysis. However, both of these could definitely be attack vectors. Maybe it did not work out for us. It could definitely work out for other domains like medicine. However, in the case of distribution analysis, one of the other things that we looked at is lexical or token level frequency analysis, inter-document frequency analysis, and extraction of unique phrases, which could lead us to the next threat vector, which is auxiliary information attack, where we use these unique signatures or lexical signatures to look up on the web and find the source documents for some of these original training data documents. These pairings or patterns could be credit agreements, dates, figures, and they did successfully reveal the original documents by a simple Google search. Now, coming to the people who will be releasing this kind of data sets, they will be probably on the white box area where you have time and resources before you release it, in which case we recommend 2 specific attacks or like threat models where we look into membership inference attacks. Since we know that these are SEC documents, they belong to a broad number of organizations which operate in the United States. And so the identification of members here is becoming very important, where you could isolate those organizations which were part of the training set and those which weren't. And this could be done using confidence scores, prediction patterns, perplexity and entropy in the case of LLMs, or other vectors. Now, these are definitely, these could be used for hyperparameter tuning, choosing the right epsilon value, the right delta value. Finally, we recommend canary insertion attacks, which are essentially integrating or pushing in certain key phrases which are unique to the original distribution or like not unique to them. Like, for example, presenting an empirical attack on DP synthetic data at PEPR, and you could put that inside an SEC document, see how well it's reconstructed when the synthetic data is generated. Finally, we recommend these 6 pre-flight checklists, these 6 attack vectors as recommendations before anyone releases synthetic data, as recommendations to test out what risk factor they pose and what risk appetite you have in the decision-making process before you release something. So, yeah. Moving on, I'll pass it on to Yash.
Yeah, so I'll just cover all the takeaway from this. So what was the takeaway? I mainly say it as 3 key points. First, sensitivity and privacy units matter. Remember that document level and organization level privacy unit thing we mentioned? That choice probably made our auxiliary information attacks a lot easier. You need to deeply think about the entity which you're actually trying to protect here and make that decision. Second, even if you have theoretical guarantees, red teaming is the true quantification of risk. DP is theoretically amazing. Math is beautiful, guarantees are formal, but execution is where people live. Real adversaries don't really care about the epsilon value if they can Google search their way through the training data. And finally, layered privacy is the way forward. Don't rely on a single protection mechanism. PI identification, proper privacy units, auxiliary information attacks, MIA, canary insertion. treat these as complementary layers, not alternatives. Because here's the thing, pets alone are weak, but pets together are strong. Thank you, and I will take questions.